It is common for any celestial object to possess a magnetosphere. Fundamentally, a magnetic field is born from simple induction. The material inside any planet is at constant motion, creating a magnetic field, which moves orthogonally to the planet's spin, creating a dynamic action. It is common and almost standard. What is not common is a dipole tilt, the angle between magnetic pole and the normal pole. For reference, Earth has around 10 degrees alongside Jupiter. Uranus and Neptune possess a dipole tilt of 50 degrees. Most of the dipole tilts are above zero and are not aligned with the poles. Saturn has a dipole tilt of 0.07 degrees, making a shiny outlier among its colleagues in the solar system. This extremely axisymmetric dipole tilt is a result of other observable features and speculations of the interior structure of Saturn. Rain, a very important natural process of water recycling which breathes life into existence on Earth. On Saturn, rain is made out of helium. Although helium rain is rain only in name, it would be hard to imagine any sort of rain in a gas giant. Helium rain is a result of immiscibility, which creates non-homogeneous distribution where most of helium is located deeper into the planet. This creates a stratified convective layer atop of the planet's core, and a helium layer of 0.1 to 0.15 of radius could axisymmetrize the magnetic field. Another anomaly we can observe on the Saturn is its hexagonal cloud at the northern hemisphere, with a radius of Earth's diameter. There is also a southern counterpart which fades in comparison compared to its northern cousin. It is more circular and unstable. Therefore, we can create an accurate model with a sample size of 2, a north and a south. In theory, a good single model can simulate both vortices by changing initial conditions. And a good single model we have the rotating shallow water model. By using the cylindrical coordinates and a gamma plane on the rotating shallow water equations, we can acquire a set of variables such as the thickness of the layer, gravity, and a Coriolis parameter. The solutions for vortices can give us the zonal velocity of the wind. Then we can fit peaks and acquire a set of parameters which are then used to create a more synthetic profile for polar vortices. This is more useful since it removes the noise which comes from the polar vortex distribution and enables a straightforward analysis of possible instability. On Earth, we have a predictable wind pattern across the northern hemisphere. This is called the Rossby wave, the pattern with which the wind moves creates a wave at a certain wave number. After including perturbations in the velocity profile and performing a linear analysis, we can acquire a favorite number of azimuthal wave numbers, and since the Rossby wave creates a standing wave, the wave number shows the number of size an emerging shape is going to have. The results show that the northern vortex is more likely to create a hexagon, while the southern vortex is more likely to create an octagon. The main difference between two vortexes is the distance from the respective poles. The southern octagon is further from its pole than the northern hexagon. There are two configurations we can use to simulate the hexagon. We can use the jet-only or the jet-plus vortex. The jet-only configuration results in the six-sided star with a counter-jet at each end. And although the azimuthal wave number is predominantly 6, the wave number of 5 and 7 are not that far away. This results in intermediate shapes at a later stage of the simulation. The jet plus vortex configuration assumes that the circumpolar jet, which one is in the middle, is influencing the central vortex. The new configuration shows visually more accurate results where simulations have successfully created a stable hexagon for a prolonged amount of time. This behavior was also shown in a lab using ink and a rotating apparatus. Saturn has two types of aurora, the normal one, like on Earth, and the one in the shape of the hexagon. The hexagon-shaped aurora stretches along the hexagon boundary of the anomaly that we described before and has an abnormal spectral image. This is the result of the upwelling, an accumulation of particles from deeper atmosphere caused by the jet. Upwelled particles give a critical data from the interior of the Saturn, and the trace particles from lower troposphere get excited around the jet and travel along the boundary. This results in the hexagonal aurora, although a definitive answer is still not available for this phenomenon. The force balancing orbit for Saturn is around 1.6 radius. However, for charged particles, this number drops to 1.5 radius due to Lorentz force. The sharp drop-off below 1.5 radius causes ring rain, where particles fall into Saturn at certain latitudes. Hydrogen particles turn into charged trihydrogens and slowly deplete ring. The most of particles come from Enceladus, a known water source, and Saturn is predicted to lose its rings in hundreds of millions of years.